This class is related to giving one example for parameter estimation where lactose is being utilized for biomass growth and some enzyme production. Basically, I'll show you the initial structure, what is the main function, what you should have. This is the main function, which will start with the function name. Those all syntax you already know, clear, CLC, format, all those things is not required. Now, essentially we are asking to have some data input, that is our experimental data. So for example, I'm running this app and I will see. So you can see our experimental data is going to be reflected here, and our experimental data is like this. I just started it. So original data is first column is with time, second one is with biomass, third one is for substrate, and fourth one is some enzyme activity produced. So these are the four columns, these are our experimental data. Now we need to know the model. So essentially we are assuming here basically that the biomass growth dx dt, I'm showing it here anyway. Biomass growth is mu max into x into 1 minus x by x infinity. X infinity is the maximum biomass concentration you can have. So it is actually a logistic model. You can have any other model as well. Then substrate consumption is simply proportional to biomass growth, and product formation is growth associated one and growth non-associated one terms will be available there. So essentially there are three different things we should come to know here is biomass, substrate, and product. So this is the differential equation. This is the differential function actually, which is normally used for ODE solver. Essentially I'll show you how we are moving. So now at this moment we know what is our original data point, and then with our data we know there are 5 different unknown parameters. For example, in this case the mu max, maximum biomass concentration, the substrate consumption for biomass, that is yield actually, and A and B. So 5 unknown things are there. These are the parameter for biomass growth related to product formation. So 5 unknown. So essentially what I am using, because all those are actually biologically relevant parameter, I understand none of them can be negative. So first I am putting a lower boundary, that is 0 0 0 5 0, because for all the 5 1 2 3 4 5 upper values is also infinity infinity infinity, and guess values means 0.2 10 0.6 0.001 and 90. These are coming for mu max, guess value is 0.2, x infinity guess value is for example 10, this is for yield coefficient 0.6, a 0.001, and b is the parameter value which I am assuming initial value 90. Of course this guess value should be taken little bit cautiously, maybe from some other paper, from other experiments, what is the expected values. It should not be very random, otherwise the solution may not be really feasible sometime. So anyway, if you know some approximate value, you should take reasonably correct values. Now the option is for the solver this is for the minimization algorithm. Options are there. So large scale algorithm will be using these values will be always interior point. Interior point means whatever boundary you are giving, all values should be tested within boundary. We want to have a display of iteration. Anyway, this option is not so serious at this moment, keep it unchanged. Now this is the fmincon function. You see fmincon function, if I'm giving, I'll just move little bit, I'll see what is my current running values. So you see now my guess value, upper limit, lower limit, and my data is actually your data, that is our experimental data, all things are there. And fmincon, the minimization algorithm, will have the input for a function name, that is function handle rather, which will actually calculate the difference between experimental and model values. We will discuss it later, what is there inside. Need a guess value that we already given. This is the guess 0.200, this one. Lower boundary already given, upper boundary already given. Those equality and non-equality constants linear are kept empty. Similarly, non-linear equality and non-equality constants are also empty. Options we have already told. And ORI data. ORI data is the original data. I want to pass it to sum square. That's why I'm adding. If you want to pass some extra data, you should pass through fmincon. So that means fmincon will go first, look into sum square. It will try to calculate whatever is likely to be calculated, and that output it will try to minimize initial guess, and ORI data will be transferred to your sum square, that function. It is a function name, you can give any function. Now let's see what is happening here. So once we continue across this line, that means it is actually transferring the control to the sum square function. You see, once I will click, you see from this function it is coming to the function SSE. What is there in SSE? So SSE function input is the parameter. You see the same parameter is coming here, 0.2, 10, whatever initial values. First time it is coming the same values, and data is always the same original data. Now that is our parameter. That means I know this is the parameter, this is the data. Now up to this 4-5 line, it is actually the simulation what you normally do. So initial time span, that is the first column values, data 1, t span. That means we will simulate this model within this time period. And initial values is for data 1 to 4. That means 0.1, 0.1, 19.67 and 0. So I'm not writing, I'm simply taking initial value. You see same values for biomass, substrate and product. Option 1 ODC non-negative 1 to 3, you already know. And OD45 the solver, which will call the OD function, the differential equation. We already know this from simulation also. So this part remains like simulation. T-span, this one. Initial values, of course I know the initial values. And para, because this para will again be utilized here. So I have to take this para from sum square, transfer it to OD45 solver. Now once we move beyond this, you will see it will come to control for dy/dfun calculation, because OD45 is transferring the control to OD_fun, which is actually calculating the differential values. You see mu max initial guess values on the initial values, it is calculating dx dt, ds dt, dp dt like this. And if I move again, that means it is going to be repeated again. So this is still going on, this control is going on between OD45 and this one. So it is just trying to solve. So I'll just skip this. So that means once the whole time point values has been solved, so I'll get the predicted values. So this predicted values means based on the parameter values we already have, the guess value of parameter what we have, based on this we are trying to find out what should be the predicted Y values of biomass, substrate and product. But you already know what is actual values, because actual values is our data. You see biomass is 0.1, 0.15 this, 19.69 substrate and 0 product. With different time you can see, but our predicted value based on this current parameter is something different. That means there is a deviation. So now we have to, because there are 3 different profiles, biomass and substrate and product, we have to make each of them the square error definitions. Actually it is not only square error, it is normalized with the square error for the experimental data also. So first we will the square error value for experimental data minus predicted data. You see the first one, that is biomass. This is also for biomass. I am making them minus, then I am making everyone square, summing them up. So this is actually sum square for biomass. We are normalizing it because maybe the sum square value for first case, second and third case may be in different order. We are normalizing with sum of experimental data and experimental data average. So that is actually sum of square error is between our experimental and model. This is in between the experimental values, that is the deviation from the mean rather. So anyway, this will be always constant because this is all experimental data. So then we are calculating E1, E2 and E3. You must know that our square value is actually 1 minus E1, 1 minus E2 and 1 minus E3. So I want to minimize these values so that our R square value will be maximum. So let's see for the first run what is SSE coming. So E1 is coming this one, E2 is coming this one, E3 is coming this one, and their sum is 0.11628. That means this is the output. So what our algorithm will try to do further, it will go back. Now the control will go back to your fmincon function, and it will try to uh, provide some new parameter values again, and it will try to recalculate the SSE. The same procedure will happen until it is going to minimize it. So you see, once our S square is over, it is going control over here again. It is going to calculate for new values, finding the SSE. Probably it will be very similar only. So this cycle will continue, and finally our para value will also change. Not at this moment, and they are going to change it further. Maybe this para is the same as original one. We'll see after some time. Of course, you see now this time the para is different one. That means it is testing with different parameter values, and SSE will be something different now. You reduced, it will continue. You see now parameter is something different, and we are going to calculate. So I'm just skipping this every time we cannot do. That means the control is coming from fmincon to sum square. From sum square, inside sum square, it is calculating the simulated values or predicted values using OD45, which needs OD fun. So it is calling OD fun. From here, calculating the model, then calculating the square difference, and that is the output for the sum square function, which the fmincon is actually analyzing. So basically we need to have here three different functions. One is the main function, one is for SSE calculator, within which the OD45 will be called, and another one is the differential function, which will actually contain the differential expression. Let's see, we will move further. Probably if we can see the solution space, finally you see, yes, so it has shown you the different runs through which it gone. Probably you can see a better way, that is iteration, function count, how many times function is being counted, the function values, fx, that is the sum of square error values rather, and feasibility, whether it is going to change, and normalization of the steps. So you can see when the function is solving, the square error value is slowly coming down, and we can see it is coming like 1.1 10 to the minus 1 finally. So local minimum found, and it is satisfied. So final sum square is 0.1102, and our final parameter is this one. So we started with some values and we landed in the optimal values likely. So once you understand this aspect, you can see this will be our actually solution approach for finding out the parameters. So we have already completed the expression, and this is the parameter estimation approach as we have done till now. So essentially with this I'll stop this video, and we'll discuss more in another one.